Yeah, this is what Ethan also mentioned, and I think Eric Blackman has various papers on this. And so, for example, they can get ordered by the normal daily relaxation type thing. They may influence things outside. They will have an active corona. But you see, the advective flux throws out both. It doesn't preferentially throw out one side in some sense.
But in one direction, I would guess you throw one side and the other side.
In the case of advection, it's not really like that. In the case of advection, you throw out both sides in both directions. But if you have a preferential throwing out of small-scale helicity flux, or if you have a preferential throwing out of one side, which is what Ethan was talking about, it can be carried either by small loops or big loops, then you will have what you are saying. In the case of advection, advection doesn't care about whether the field is small scale, large scale, whatever it is. It's just taking the whole field out. And if you're conserving the field, the helicity in the disk, okay, then when you advect it out, you have still got the net helicity 0. But you have an interesting situation. You have got the scale separated helicity and it has to relax in some way. And maybe it will relax by still ordering itself more. I mean, this is something which I think is an interesting thing to explore.
Can do. Interesting moment that this flux was in our paper with Alexander Zumaikin. I mean,
82.
82. But what's interesting? It's interesting, but not so interesting. Interesting is sometimes these two velocities is not equal. I mean, real mean velocity is effective. I don't remember what's the coefficient, but sometimes they have, maybe it's important. Two short? Okay.
Which two velocity?
Velocity, effective velocity. If you take into account gradient of potential and to make some calculation, this effective velocity will not precisely the same as real velocity. It is effective. And sometimes it may be some coefficient.
No, I agree. See, for example, that isotropic thing where I'm saying everything is advected out, yes, comes only in the isotropic limit. Suppose your magnetic field thing has anisotropic, yes, pieces, then you don't get the helicity density being transported out. That comes in the limit of isotropy. The advective flux is of that form in the isotropic limit.
What can I say? Strictly speaking, if you've got how to say, is imposed large-scale magnetic field. No, again, asymptotic result. If Reynolds were very large, my feeling that in this situation, these two velocities are not the same because your magnetic fluctuation anisotropic in presence of large-scale magnetic field. It's a point.
Yes.
Maybe it's important.
Again, I would like to just try to find something that could be tested for observation. So I have a principal problem with this idea. So if I understand correctly, that galactic wind, so a strong wind, would then inhibit the dynamo action in the disk. Whereas on the other hand, our best example of an adjoint galaxy shows exactly the opposite, a very nice axisymmetric dynamo field in the disk and a very strong galactic wind of the order of 250 kilometers per second. So
but the galactic wind is in the hot gas or in
the wind is seen in the cosmic rays. So it's also seen in the hot gas and also the warm gas. So it seems to be a wind which transports all components of the
So you have to convert those numbers into those parameters. So you see.
But I understood correctly.
No, I understand. I understand. What I meant was, if you require in this, at least if you are thinking about advective flux, you require some advective flux. Okay, what is that sum? The numbers which Anwar used was like 100. Anwar. I think 100 kilometers per second or something, and 0.10 to the minus 3 density for the hot gas density, right? That's the number that you use. 100 kilometers per second. So maybe it could well be that guy may work on problem could be in the case of those guys who do not have any such bin. Okay, then what happens?
I put it slightly differently.
Yeah.
Organic field is producing the gas, right? To the lowest approximation, it's frozen into the gas. The wind doesn't remove all the gas from the galaxy because we see the galaxy, it's there. This visit will remove all the magnetic field. Don't need to worry too much.
Yes, it's true.
But you have to do that properly.
There is an optimum speed which is the best for the dynamo. If the wind is too strong, it will destroy everything. If it's not there, no, this color is changed.
But again, I'm just complaining that these models are around since many years and we did not yet sit together and do really...
This model is not around for many years, by the way.
There, so I think we should really do that.
I agree. This model is not around for too long. I mean, it's only for a few years. The advection model, which is only there for, as you see, 2006 is the paper. So. Yes.
I just would like to support your comment on the importance of tau, the value of tau in the tau approximation. I mean, when you look at the effect of shear flow using tau formalism, the tau will depend on the shear flow itself. So I think we need to be a little careful. Unless we did something more, our prediction was that the shear flow, as long as it's stable and as long as it's parallel to the new magnetic field, it will pinch down rather than torsion.
But this is post-torsion, yeah?
Yes, so I mean, I'm saying, so,
Yeah, you have to do it carefully. That's why don't.
so you expect the alpha effect will increase as you unhook the shear flow.
No, he gets a different effect, sheer current effect.
Yeah, I
Nothing
mean,
to do with alpha.
yeah, of course, I mean, there will be some other effect, omega 0 plus effect or something. But as long as you do not have those other effects, if you just consider the alpha effect of the differentiation.
Regarding direct numerical simulations, there is not yet a simulation which has shown the advective flux to work, but this is a restriction of what has been done so far. So nobody has really tried very seriously yet. But the fluxes that have, of course, been seen very clearly in the simulations that have been done so far are the Wishniak and Cho fluxes. So they have been seen quite explicitly by directly measuring the flux in the simulation and also by seeing the effect of these fluxes in terms of alleviating the catastrophic quenching. What we expect is that these Wishniak and Cho fluxes actually correspond to what is seen as coronal mass ejections in the sun. And then it's a question to the observers like you. Do you see coronal mass ejections? And if I remember some longer time ago, there was no hope. But now I believe some people are beginning to see things like coronal mass ejections in galaxies. And that is exactly what we would expect and predict, more than perhaps the wind. So, what?
In synchrotron we see something that could be interpreted like that. Also in X-rays, I think these things are seen what could be. Didn't we people to call them similar to coronal mass ejections, but I think that there are interpretations of possible.
And then one needs to measure the helicity flux, of course, in these objects. For the sun, we know that the helicity flux through coronal mass ejections integrated over one solar cycle is on the order of 10 to the 46 Maxwell squared per cycle.
Sorry, Axel, I just respond to both things. One, I think, I mean, you should, you may not have seen it, but it looks to me much simpler as advection than any other thing. Because everything else, you may see it in the simulation, but at least calculating it, it requires some closure and all this. But there is no reason for all the fluxes not to exist together. Okay. So for example, this thing which I skipped, Sharanya's, this thing with the, this has got both advection and the Wishniak and Cho flux. And you have, of course, we wrote this paper with Wishniak and Cho, so this one has both. And actually, if you put in the Wishniak and Cho, then actually things which are decaying originally with this advection can be lifted back, and things which were, so it obviously enhances everything. And in fact, what is difficult at present is to actually saturate. Once you let ethan loose, It's difficult to keep him down. So this is the problem that we are having. And so that is, so it is possible that there is this both, whole range of things one has to think about. And so it's not clear that you need only like corona. You may, even the galactic wind may help. I mean, it's not necessary that only coronal mass ejection type events are required to get rid of the flux.
So, thank you. I think we stop here. Now the time is to have a discussion.
Yeah.
What time is the campaign close?
You want this?
Okay. I suggest to discuss.
A little bit louder.
Okay, I suggest to discuss several questions.
You want your mic?
Okay, the first is the non-helical shear mean field dynamo. Non-helical means that mean helicity equals 0. Here I make some table of facts concerning this issue. Okay, from the point of view of theory, the first effect, shear current effect. The second, shear homogeneous alpha square effect. The third is incoherent alpha effect. Okay, we need to fill this table. I separated these two effects because I see this as a different effects. Okay, now, so this is references. Okay, now, concerning this effect, shear current effect, this is the growth rate of the growth of the large-scale magnetic field, and if Kz is independent of shear, so growth rate proportional to the shear. Okay, but for maximum growth rate, Kz is proportional to the shear, and we obtain S squared. Okay, so maximum growth rate scales as a S squared, and growth rate scales as S. Okay, this effect has been, for studying this effect, it was applied several procedures. For small Reynolds number, SOCA results. The paper by Redler and Stepanov doesn't found this effect in the frame of SOCA. And Rudiger's statement, Rudiger and Kitchener studied this effect, and recent Rudiger's statement was that even in small Reynolds number and small Prandtl number, this effect exists. Our preliminary studies also confirm this already. Okay, tau approximation, generalization procedure found that this effect exists, and test field simulations in the range of parameters haven't found this. Now, the second effect, shear and homogeneous alpha square fluctuations. They also have the same growth rate, the same form of the growth rate. So, growth rate depends linearly on shear, but the maximum growth rate when Kz depends on S is S squared. So, this effect cannot be found in this procedure. It was found by some phenomenological procedure applied by Mike Proctor, and in test field, this effect, okay, if we separate these two
It
effects,
was found.
I put here a minus. Okay,
I think you should put a plus there, really, because I think Axel was...
okay we will,
Yeah.
we will discuss it. Okay,
The diagram,
now,
so I should use it correctly.
invariant alpha effect. Okay, I put here question marks because at least in the frame of SOCA, tau approximation, randomization procedure, this effect hasn't been seen. Yeah, so since each, okay, now the other facts, direct numerical simulations. Simulations by Axel 2005 found that there is large-scale dynamo with sinusoidal constant in time and sinusoidal in space, also. And also recent simulations in the shear box also found dynamo and scales, scaling of growth rate versus shear is growth rate proportional to S. Okay? So, discussions, please? Yeah,
No, my comments very simple. In some sense, shear dynamo, non-helical dynamo is fact. It's, I guess all people agree, right? Shear without mean kinetic helicity. Is it possible or not?
This is fact, yeah. It follows from numerical simulations.
So shear dynamo is a matter of fact. Another story, what's the real mechanism? As I understand, for us a little bit difficult to explain why Yosef, Tarik Yosef, and we find S squared, not S. I believe maybe the reason that it's not maximum growth rate simple. Another story, generation of vorticity.
Yeah, but why should the vorticity matter?
Sorry?
I mean, why should the vorticity... You mean that the vorticity dynamo actually generates the magnetic field dynamo?
Yes,
Okay.
new.
There is a mixture. So this in principle, these two experiments are not clear. You said that this setup doesn't correspond exactly to theoretical setup. Because in theoretical setup, up to now, it was not studied the situations when there is a growth of large-scale vorticity and there is a growth of the large-scale magnetic field. So we have to use in DNS to find very clear situation which corresponds to the theoretical. And also, from the side of theory, we have to study situations, growth of magnetic field in the presence of growth of vorticity. Of course, these two objects have different growth rates. The value, for example, growth rate of vorticity is much larger than the growth rate of the magnetic field. Yeah. And please?
So why are you distinguishing the second and the third column?
Sorry?
I'm a bit confused. Why are you distinguishing the shear?
Oh, okay. Why these two effects? Okay. When we speak about this effect, it is clear mathematical setup. We have two forcings which are separated in scales. One forcing produces in small scales magnetic velocity fluctuations. In a larger scale, there is another forcing which produces kinetic velocity fluctuations. So, all theory is based on the double averaging. One averaging, this is just the equation which has been discussed by Nikita Sokolov, and mathematical justification of this approach has been done in his paper. Okay? So, when we speak about this shear homogeneous alpha square, we speak about the exactly Krigman setup. Okay?
No, but once you have a finite system, does it matter that once you have a finite system,
Finite, yeah.
like a galaxy or
Yeah.
the sun or whatever, there will always be fluctuations. they may not have the longer time scale and they may not be enforced by anything other than the fact that it's a random system.
Yes.
They may have the same time scale as the information time or eddy turnover time. Or whatever.
Okay, but if we would like to compare theory with DNS, we have to compare the same setups. I mean, a theory has been developed only in the case where there is a separation between two forces. If there are no separations, theory cannot be developed. Or, I don't know, at least, I don't know any theory which...
difficult to build a theory,
yeah,
definitely.
So, this is the reason why I separated. Also, if we consider the paper by Eitan Vishniak and Axel Brandenburg in 1997, the theoretical description is different.
I understand.
They use second movements.
In practice, what will happen?
Sorry?
In practice, what happens
Yeah.
is that either if you're doing a numerical simulation or you're thinking about some physical system, you want to, let's say, find alpha, and you're making some average over some space.
Yeah.
Okay.
I said that there is a problem.
Right? Now, if you do not also make, if you do not make an average over all volume and all times, you're always going to get these fluctuations when you're.
Yeah.
So one thing would be to just stick in something with fluctuations.
You know,
Those two things are the same.
in some sense, this setup is in some kind of artificial. It's not so easy to find in practice this
So what is my
Dragon setup for the
which one?
alpha fluctuation.
Big one.
Do you think your paper is number 2 or number 3?
It's both.
Or both, yes. I don't know.
Certainly, no, it's true. Certainly the question mark in my column at the bottom should be a plus.
Sorry? Question mark where?
Yeah, just up there.
Here?
That's a plus.
Okay, if we...
Just put it in.
Let's see
When
the-
you wanted to fill it in, then fill it in. No. This is the whole point. Yeah, that's right. And also the last, yes, that's a plus. And also the last column in the middle, Axel, tell him it's a plus.
That's in the middle.
The last column. The middle row, the last column. The
Just
last.
do
Last.
simulation.
That's a plus.
This, okay.
Yes, it is. Yeah, you just make that a plus.
Okay.
You make it bigger, I think.
Okay, big. Big plus and small mean.
Ah, that's very good, yeah.
Okay.
Wonderful. Now, do we have some, okay?
If you start to correct this plus and minus, could you please also change just put only one plus for shear current effect and soccer result, because
Okay.
we definitely
Radion
show
wants that I put here, okay,
yes, bigger,
here I
is
put
bigger.
here Frankl much more than unity, and here
Minus
minus,
huge. No.
okay? Yeah, you're right. Okay.
So
What else?
half of plus from Rudiger, half of plus for us.
Yeah,
From
okay,
us.
now, maybe if there are no any other comments, we'll come to the next question.
Maybe you should clarify this result by Günter Rüdiger and Kitatinov.
Okay.
I thought they have a minus.
Yeah, in their paper, it is not clear, this conclusion, okay? But several times when we spoke with Günter Rüdiger, he said us that he personally found generation of large-scale magnetic field in the presence of small magnetic particle number. And after that, we also study with Nathan, we started to study situation with second-order correlation approximation, and we really found there is some non-trivial point in that this procedure using using turbulence and shear. Okay, maybe we will postpone discussion on this at the another conference. There is several non-trivial things. Okay, Okay, so let me postpone this discussion.
Do you mean in calculation in soccer?
Yes.
Soccer method?
Yeah, I mean,
Just
soccer,
if you-
Not
the
only
presence of
soccer.
shear.
It's better if you find out something new or you find the mistake, just publish your
Of
results,
course.
then we will
Of
put
course.
the plus there.
That's the reason
We'll
I,
do it,
okay,
we'll
that's
do
the
it
reason
very
I
quickly.
prefer to give a reference to Günther Rüdiger, and we don't discuss our.
You're aware that he made a mistake.
Yeah, okay. Well, maybe let's. Do you? Somebody would like to discuss this issue, or we'll come to the another issue.
Why does Isa not say anything?
Yeah,
I have to say that my jet lag is so bad right now. This whole thing looks like this gray field.
Okay.
No,
Okay. Actually, situation is the following. The non-chemical shearing field dynamo is an open issue. Okay? It's not clear with this kind of dynamo, and so in this program, we are going to make some progress in that direction, and also during the future.
I do have
1
one
year,
thing-
we are going to study very.
I do have one thing to say.
Yeah.
And that's that the thing that I find most confusing about many of the numerical experiments, the argument about the small-scale dynamo versus the large-scale dynamo, is that in any realistic system with a relatively small number of eddies, it's clear that the fluctuations you get, just from the fluctuating electric field contributed by different eddies coming together randomly, are going to make an unambiguous measurement of a mean field dynamo difficult. And I would like to see people be much more careful about what level of magnetic field they're aiming at see in their experiments, because typically in most of them you expect to see a lot of noise.
Yeah. But if there is a parameter range when small-scale dynamo is absent, and this is more clear situation, yeah?
Absolutely.
Yeah,
But it's
okay,
not a, it's
I
not a
agree
very
with
astrophysically interesting
Yeah,
situation.
yeah, of course, yeah. Okay.
I mean, the level of magnetic field that have been reported in the experiments with fluxes, they and shear are energy-wise on the order of 50% at least. So the 50% of the magnetic energy is contained in the averaged field. And an averaged field means a toroidal average. Still dependent on X and Z in that case. So that's fairly strong.
I know, but
And that's
you know, but we
sort
made
of-
a fairly what I think was a fairly good argument for that you could get that even in the absence of any systematic mean field dynamo.
From the fluctuations, I mean, yeah.
Yeah, but at least we know now that several very strong groups are trying to perform direct numerical simulations, and so I think we will get additional information during this year. At least there is a very active group by Alex Chikachin, Axel, also Etan group, which simulate these problems. Also, I strongly hope that simulations by David Hughes and Steve Tobias also will find non-helical large-scale dynamo in the presence of convection. At least theoretical predictions show that convection causes positive contribution to mean field dynamo. Okay, so they need to perform, to have a parameter scan in the different shear numbers. Okay, maybe we'll come.
Igor, can I just ask as a non-specialist,
Yeah.
everybody, when you're speaking about shear, speaking about helicity, what about angular momentum? I never heard. I mean, has anybody looked at the effect of that?
No, there is angular velocity index.
No, the total angular momentum not equal to zero. So this kind of thing studied, right? And so what effect does it have?
That that regular shear is what produces one loop in one cycle in the dialectic dynamo case. The fact that things are rotating is making the finding of the colloidal to toroidal field.
So does it make dynamo stronger? Or?
Yes, that's.
Yeah,
Yes.
but it's not enough for dynamo.
Yeah, it's not enough for exponential growth, and that's where all the alpha and the shear current and all these things are coming. Because it's only will produce linear growth.
Yeah.
Differential.
It would, whether you have angular momentum or not, it greatly affect the flash scale spectrum. I mean, even without any dynamo, you either.
Okay, I mean, in most cases, except for maybe rapidly rotating stars, it must be small effects in that sense.
So, Axel, in the simulation, okay, you believe that in this approach, gamma scales as okay.
Even for
because it is not directly follows from your paper published with Karl-Heinz Redler
I'm just
in
looking.
2007. Yeah, recently. Yeah.
Let me ask.
Okay.
I've got more question to Axel in this situation.
Yes.
What kind of gamma have you found in your calculation? Similar, Igor mentioned on this blackboard, is proportional to S. Gamma proportional to S. This one.
Yes. Gamma proportional to S.
Yeah, but nevertheless, in frame of this equation, maximum growth rate proportional to S square might have effect. Or you don't find it, or.
Let me think. I need to think about it.
Yeah.
Okay. Let us discuss.
Okay. Now, what about small scale dynamo? Okay, in small scale dynamo, for small quantum number, it was a great question about the existence of such dynamo, at least up to the 2007, but very careful numerical simulations by Alexander Shikachikhin with company published in two papers, one in Physical Review Letters and other in Journal of Physics. They show clearly that there is small-scale dynamo for small quantum numbers, and they found that this kind of dynamo is different from that of for large magnetic quantum number. Okay, now today it was demonstrated another approach for analyzing of small-scale dynamo and structures in small-scale dynamo. This method produces, at least by the order of magnitude, the threshold for generation of large-scale magnetic field, small-scale fluctuations, the threshold in magnetic noise number, which is of the order of the threshold which was predicted by the theory. Yeah, and do you want to discuss this subject? Yeah.
I think the idea and the reason that Alex Sheehan proposed is reasonable. That means, that is to say, the dynamo, the small-scale dynamo, peaks at the resistive scale, and at small magnetic Prandtl numbers, this resistive scale is exactly where there is this bottleneck effect of the turbulence. And there the velocity field is rough, much rougher than in the inertial range. And so as long as we are within the regime of the bottleneck, the small-scale dynamo will either be very hard to see or will not be seen. Then if you go with the magnetic Prandtl number even smaller, 0.05 for example, the hope is that we are out of the bottleneck and we see the small-scale dynamo again at a certain magnetic Prandtl number, which we still don't quite know how big it is. Maybe on the order of 200 or something. Yeah. Patrick may want to say a few words, because he has done simulations at very high resolution, direct simulations.
Yeah, well, we don't have high enough resolution yet, so we do get a small scale dynamo at Prandtl number 4.1.
You don't?
We do.
You do? So his biggest resolution is 1,500 cubed. 1,500 cubed. Not 2,000 cubed yet.
No, it's still 1,000 cubed.
It's 1,000 cubed even only, yeah.
So Axel, what is that bottleneck you mentioned? I mean, is it bottleneck for magnetic energy?
No, it's for kinetic energy. And that's, of course, something which you don't see in the shell models.
Okay, so, but for magnetic energy, so, I mean, will it be as well bottleneck?
Nobody has seen that yet. We thought, I mean, remember we got in 2003, we got a magnetic energy spectrum which was, of course, not over a terribly long range with 1,000 cubed mesh points, but it looked like k to the minus 3 halves, while at the same time the structure function exponent for the third moment was 1, suggesting, therefore, that the spectrum should really be k to the minus 5/3. So the departure from minus 5/3 towards minus 3 halves, we interpreted it back then as a magnetic bottleneck effect. But that is, of course, a very big argument.
Is it very clear distinguishable 3 halves or 5/3?
Reasonably clear, yeah, but of course, you don't know how it's being perturbed by the side effects that you don't see yet. So one of the things is the bottleneck effect, but the other thing is that you see a steeper spectrum in the kinetic energy to the left of the bottleneck. It's not minus 1.7, which would be the 5/3 plus a Scheele-Weck correction, but it's actually 1.77. And that has been found not only by us, but in particular by Kaneda et al. At 4,000 cubed. Right. So if you do expect spectra which have a very strong correction of minus 0.1, and then another correction of plus 0.2 or something like this, and then you average the two together by not resolving these different correction regimes, then you may, of course, get this 5/3, which is simply not meaningful enough as long as we haven't been able to distinguish this clearly from the inertial range, or the subinertial range where the driving occurs, and the dissipation range.
Pull down the screen, yeah? We can make the bigger screen.
We can keep here.
This is our.
No input. You want to show this, yeah? Can you?
Yeah. I'd like to show this. Yeah.
Okay, maybe you should project again. Is the signal? Yes, works.
Okay.
Unbelievable.
Okay. This is graph from the paper by Kachichin and company, which shows the growth rate versus magnetic quantum number. And maybe this question also is interesting in connection with your work on small-scale dynamo. We see that from the graph that even for small magnetic quantum number, it was detected generation of large-scale magnetic field. It was detected generation of small-scale fluctuations due to small-scale dynamo. So you said that you can't yet reach this parameter range. I mean this parameter range, yeah?
No, not yet. Not for small enough quantum numbers.
Okay.
It looks like he used hyperviscosity.
Yeah, he did, of course.
He used also viscosity and without viscosity, just comparison.
There's only one aim to suppress bottleneck.
What?
It's aim of super viscosity this calculation to suppress the effect of bottleneck.
No, you don't suppress it. You make it actually even stronger, but you are able to go more easily beyond it already. That's the hope. But certainly, if you Prandtl 0.1, I don't think that.
It is, and also it is seen here from this diagram some results which are consistent with your simulations, where it was found that in diagram magnetic resonance number versus relay number, we don't go in this way, but it goes in the plane. Yeah. Okay.
So is it clear that hyperviscosity doesn't change physics?
Yeah.
It's not.
Okay.
No, it's not clear, and therefore, of course, that's the reason why people are doing is a direct simulation.
Yeah.
It's just very hard.
But as far as I remember, it was also the question of Gregory about this, and they performed some justification for this. They performed some check for this. Okay, Sergey, maybe you would like to discuss.
I think everybody's hungry.
Yeah. Okay. You have some suggestions?
What did you want to?
Okay.
I'm totally happy with all the issues discussed.
Okay. I would like to send organizers to a very, very interesting conference, and was
Hello.
yeah, it was very interesting to be here. Okay.